So today we're going to finish off our discussion of signal space. What we're going to do is we're going to start talking about two-dimensional signal space. So before what we had was one basis vector, call it S, and all of our signals were aligned with S. So for instance, we had S0 out here, S1, S2, so on, S-2, Sn-1. So what we showed last time was that there's a geometric way to think of the matched filter. So really what you're doing with the matched filter is you're taking the dot product. And what dot product is the projection. If, let's say this is the detection filter, the dot product is really the projection of each of these signal vectors onto the filter direction. So for instance, you can decompose each of these vectors into a component parallel with the filter and a component orthogonal to the filter, like that. So it should seem obvious that the way to maximize the distance between all of these projection points. So obviously, if I took projections like this, these are much closer together than these are. And the way to maximize that distance is to align the axes so that the filter is parallel with the signal vector. So, just to quickly review, let's do a 4-area example. Or excuse me, let's do an 8-area example. We did a 4-area example last time, so let's do an 8-area example where S of K is polar NRZ signal. There's NB of these. Now, what I require for my vector, for this vector is that I can translate this into a vector S, which is equal to some constant for every element. But what I require is that norm S equals 1. That's the feature of the signal space basis vector that allows us to, if we translate that directly into the matched filter, that just allows us to pick off the coefficients. Okay, so if that's true, then what are these amplitudes? We said this last time. So we need norm of S to be 1. If these are all 1, it's worth pointing out that in that case, the norm of S squared, which is equal to S dot S, is 1 times 1 plus 1 times 1 plus 1 times 1 plus, and so on, up to
root n.
yes.
S squared.
This is NB. So you can think of this as, in order to normalize this, what we have to do is basically divide by the norm. In fact, I think I said this was root NB last time. That's actually not correct. It should be 1 over root NB. Then if I do that, I get 1 over root NB times 1 over root NB plus 1 over root NB times 1 over root NB plus and so on. Repeated NB times, so then I get 1 over NB, 1 over root NB squared is just 1 over NB times NB, which is 1, which is what I need. In other words, I'm pretty sure I said that's root NB last time. It should be 1 over root NB. Okay. So let's let that be the basis vector. So that's S. And let's select 8 signal points along here, the origin here. And what I want is I want the distance between adjacent points to be 2. The distance here is 2. If this is the origin, then S3 should be +1 and S4 should be -1. If this is 2, then what is S2? +3, +5, +7. And here -1, -3, -5, -7. So, last time we had that probability of error, the probability of symbol error is equal to m minus 1 over m, or c of d over 2 root 2 sigma squared. So let's let d equals 2. And let's let d equals 2 because the distance between adjacent points is 2. Remember, this only holds if all the points are equally probable, all of my decision thresholds are halfway between the points, and all of the distances are the same. Let's let d equal 2, and let's let sigma squared equal 1 over 8. So in that case, what do we get? We get probability of error is equal to 8 minus 1 root 7 over 8, or C 2 over 2 root 2 times 1 over 8, which is 7/8. Or C, that 2 cancels with that. This becomes 1 over 4, root 1 over 4 is 1/2. 1 over 1/2 is 2. So that's 7/8 ERF-C of 2, and ERF-C of 2, if you go to MATLAB, is 0.0047, roughly. And if you multiply that by 7/8, this divided by 8 is roughly 0.0006, times 7 is 0.0042. So that's the probability of confusing any two symbols. Okay, what's energy per bit over here? Energy per bit is energy per symbol. Let's start with that. I have 8 symbols, so it's 1 over 8 times the sum of the coordinate values squared. We've already established that the energy in the basis signal is 1. So if I scale that basis signal by, excuse me, it's TS over 8 times sum over all of the coordinate values squared. So if I scale the basis vector energy is TS times its norm, which is just 1. If I scale that by any constant, then the resulting energy is that constant squared. So I end up with TS over 8 times sum over the alpha I squared from I equals 0 to 7 is equal to TS over 8 times, well, I have minus 7 squared plus minus 5 squared plus minus 3 squared plus minus 1 squared plus 1 squared plus 3 squared plus 5 squared plus 7 squared